Okay, so hello everyone. I'd like to thank you all for signing in for today's seminar. Our speaker today is Professor Chris Combs from the University of Texas at San Antonio. As you may know, late last year, the University Academic Alliance of Taiwan, a group of 11 public universities in Taiwan, signed a memorandum of understanding with the University of Texas system for collaborations on a variety of topics, including semiconductors and also space technology. And so right now at the University of Texas at San Antonio, UTSA, they're in the process of setting up their own aerospace engineering program, as well as their own space capacity. So it's a great privilege and honor today to have Professor Christopher Combs of UTSA joining us. So Professor Combs' background is in hypersonics, and he's also tasked with establishing this new aerospace program at UTSA. So my understanding is Professor Combs will be talking a bit about what's going on at UTSA right now, possibilities for future collaborations or exchanges, and also giving us a better understanding of his own research on hypersonics and implementing related test facilities. So Chris, it's all yours.
Exactly. Yeah, thanks for the introduction and appreciate the invite. And like I was saying, thank you guys for working late to stay up for this one. All right, I'm going to try and share my screen. Hopefully this works okay. All right, yeah, thanks. So, all right, kind of like Lauren was saying in the introduction, I'm going to give some background on UTSA and what we do, some of our aerospace program trajectory, and then get a little bit into the hypersonic stuff that I've done. I'm going to try to avoid getting too into the weeds and too technical today. But that's kind of the general outline of the talk. And we're going for about what, 50 minutes or so. Okay, perfect. So before I get started, I always like to acknowledge we've got a bunch of different sources of funding, especially related to the technical work that I do, whether it's the Air Force, Navy, DARPA, NASA, the National Science Foundation. There's a Joint Hypersonic Transition Office that we work with. And then, as many of you all know, the students are the ones that do all the work. They put the sweat equity into the lab. I kind of cut them loose down there and let them do their thing. And so any of the results that you see, really all the credit goes to the students. And even the wind tunnel facility I'm going to talk about, that was built entirely by UTSA students. So big shout out to them. And this is just a handful. I've got a lot more in the lab, but these are the ones that kind of led the work that I'm going to highlight today. So some background in UTSA, if you're not totally familiar with us. So we are what's considered a Carnegie R1 research institution, which is the highest research activity classification that we can have in the US. And we're a growing institution here in San Antonio, 35,000 students. We're what's called a minority serving institution because 69% of our students are underrepresented minorities traditionally in the US education system, a bunch of first-gen students, a bunch of military affiliated students. And if you've never been to San Antonio, it's a city of over 2 million people, a really vibrant culture, a lot going on. So it's a really excellent student base for our programming. And we've got several different accredited engineering programs, and I'm in the mechanical engineering department. Aerospace is embedded within mechanical. We have biomed, chemical, civil, computer, and electrical. And the whole place is just growing really fast. So yeah, we're just almost at 35,000 students. Almost all of our students are from Texas. And we also have a unique number of military affiliated students. San Antonio calls itself Military City, USA. And we have a bunch of veterans in the programs, which makes for, a lot of mature students and students with some interesting backgrounds and experiences that can really contribute to the type of work that we do. So it's been a really rewarding place to be, and it's a great place to create opportunity. So I like to also give some background on just the state as a whole. And Texas is really an epicenter for aerospace in the US. It's the #1 state in the US for skilled aerospace employment. Pretty much all the major OEMs and manufacturers have a location here. We've got 15 military bases. 3 of them are in San Antonio, and they comprise Joint Base San Antonio, Sam Houston, Lackland, and Randolph. Obviously, NASA Johnson, Mission Control, Houston, we have a problem. That's right down the road, a few hours away. The Army Futures Command is headquartered in Austin. We've got SpaceX, Blue Origin, Firefly, all close by. And so it's a really major aerospace sort of community here in Texas, and a lot of opportunity for students, a lot of close connections to really pretty much everything that's going on, and all the different major companies in aerospace. So we're really trying to grow in that direction, because before I got to UTSA in 2018, and before I got here, we didn't really have an aerospace program. It was kind of a targeted area of growth. So I was given basically a mandate to grow this program out. And so we started with an undergraduate certificate program in fall 2019. My argument kind of was that if you compare undergraduate degrees in aerospace and mechanical engineering, the difference is primarily a few different classes when students specialize at the end. Maybe some of those classes along the way are sort of tailored more with an aerospace flavor, but when it comes down to the core content that you're learning, students don't diverge that much till right at the end. So we created this certificate that gives students the opportunity to have those electives. They're sort of in their senior year and get an aerospace certificate that goes along with their undergraduate bachelor's degree in mechanical engineering. And then we have a master's graduate certificate that rolled out a couple years later. And then we also had a master's degree program that we introduced a couple years ago in aerospace engineering. We've got a PhD program proposal that's sort of routing through approvals right now, and that should be ready in fall 2025. We'll be offering our first PhD degrees in aerospace engineering, and the next step is going to be a bachelor's degree, which is really the most involved in terms of the legwork to get that done. So we've got about 1,000 students just in mechanical engineering. There's almost 5,000 in engineering here at UTSA, and we've seen just a lot of interest in aerospace. I don't know if many of you are involved in AIAA, the American Institute of Aeronautics and Astronautics. We opened up a student chapter. There's about 50 students. They just went to Southwest Research a couple weeks ago, and then they just went to Boeing to do a tour there last week. So they've had a lot of stuff going on. They're building drones right now. And like I tell people, we had over 50 students involved in the design of the wind tunnel that I'm going to tell you guys about. And our graduates are really already all over the place in aerospace. So they're doing really well. We've got a bunch of local support. We have a new hire that we're kind of negotiating with right now that's got more of a space focus. So I'll kind of give you some background on our coverage areas right now. And then I'm always pushing for more hires. We've got an opportunity for clusters coming up next year. So these are some of our core faculty right now. We've got people in materials. I do aerodynamics, and particularly high-speed aero and hypersonics. And we've got computational fluids folks. Daniel Pineda does rockets and propulsion. We've got a really strong astronomy group and astrobiology emphasis over in the College of Sciences. And then we've got on the electrical engineering side, communications and GPS and controls folks, robotics people, and some UAV drone specialization as well. So we've, from not having anything really about 6 years ago, we've already grown this fast. And this is kind of outlined in a different way here, some of the same stuff. But as you see, aerodynamics and fluids, materials, propulsion, controls and drones. We've got some batteries folks. That we have the whole earth sciences, remote sensing side of the house. We just opened up a new college of AI and computing. So there's some strong expertise there. We have the planetary sciences, and we had a faculty member that just made a bunch of press for some discoveries she made on Titan. The uncertainty quantification and V&V is a really important part. And we have a group that focuses really just on workforce development and education. But the thing that I've kind of highlighted as a big gap is our satellites, orbital mechanics, and space mission design, which I understand is actually a strength of yours. So it's maybe a nice area for potential collaboration, because you can help us out where we've got a gap right now that we're still trying to fill. One thing I like to share is that I'm the director of a NASA-funded center called CAMI. It's the Center for Advanced Measurements in Extreme Environments. And sort of the goal here is to act almost as an umbrella to tie in a bunch of researchers in these various disciplines that I just outlined, where the original focus was sort of what we called extreme measurements in NASA-relevant applications. So for me, for example, hypersonics sort of comes into play in the reentry part of the space environment, sometimes on ascent a little bit. But it's that sort of moniker has allowed us to bring in a bunch of people from these different areas and get them connected and working together. And it's grown into a much larger thing than sort of the original plan. And we got hundreds of students that have been impacted. We do 1 to 2 outreach events a month, getting in the schools here. It started with 5 core faculty, and now we've got over 30 and an admin that's running support. So that thing has grown really well and really grown beyond the original NASA funding footprint that we had. I want to highlight Daniel because he's got this laser spectroscopy and chemical propulsion lab. He's building a shock tube that they just finished up to look at like fuel mixes and fuel chemistry. He does a lot of diagnostics development, which is there's some overlap with some of the stuff that I do, and combustion work, rocket propulsion, rotating detonation engines. So that's a really nice capability that we've just built up, and somebody you're probably going to end up hearing from at some point. We also have this unique drone enclosure, which is one of the largest ones at least at a university in the U.S. It's 150 feet by 100 feet by 60 feet. You got some people for scale down here at the bottom, and it's open for use now. Basically, there's a committee of us that make sure people are handling it the right way. But the motivation for a drone enclosure, if you don't have a lot of familiarity with drones, at least the U.S. regulations are that you have to have some licenses and approvals to be able to fly your drone outdoors. And so if you want to be able to do especially research things unrestricted, that's mostly limited to labs indoors because FAA regulations won't permit that much experimental work without a considerable amount of paperwork and licensing. So what you're able to do we've built this drone enclosure, which is basically like an outdoor lab. And so once you're inside the drone enclosure, the FAA outdoor rules don't apply. So you can really have a lot of space to do work with drones, conduct research, experiment, do training without having to make sure everybody has a license. So that's been a really nice capability that we've already had some events come out there and do some great work with drones. And so where we're headed, there's some stuff I didn't get into, but there's really a big push from U.S. federal agencies, whether it's the DoD, Space Force or Space Command or the Air Force, and of course NASA, as always, with like the Artemis program, pushing space. Texas is right in the middle of that, and there's actually been some Texas legislation to push more dollars into space funding. And we feel like we're in a good spot to try and leverage our current expertise and continue to grow because of the student body that we're serving and the demand that we're seeing for aerospace. So we're really trying to spin this thing up, continue to grow it fast. And we have all these faculty here, and there's just an effort in organizing everyone that we already have and kind of vectoring towards space. But we're looking for opportunities like this one as well to figure out who we can collaborate with, who can help us, who can help us grow, who can we contribute to, and try and find ways that we can help your programming as well. So we've got, like I said, new degree programs that we're going to try and develop, new courses that are coming out. I'm teaching hypersonics this semester for the first time, which has been a blast. And so we're trying to continue to grow, add more electives. And like I kind of alluded to, we're going to be adding a lot more faculty. And now I'm starting to tell anybody that'll listen that we need to build a new building for this. So that's going to be a ways down the road, but that's kind of where my head is to give you an idea. So that's kind of the general aerospace overview for UTSA. And I'm going to start to narrow the focus into the work that I'm doing and my research. So I've got a pretty good sized group. We've got about, 15, 16, 17 grad students. We're close to 30 total when you add in the undergrads. It's a mix of PhD and master's students, probably skews PhD heavy. And like I said, a good number of undergrads working in the group too that we pair up with the grad students. And they work really hard. They're a lot of fun, good students. And the focus of our group is, like I said, high-speed aerodynamics and hypersonics. And just to get everybody on the same page, I kind of like to define this stuff. If you've heard things in the news, which you probably have, about sort of what's going on in the world with hypersonics, usually the easy definition is Mach number greater than 5. And so when we're talking about Mach number, that's the ratio of your velocity to your speed of sound. So Mach 1 is when you're flying at the speed of sound. When we're hypersonics, people usually use Mach number greater than 5, which is, a nice convenient term, but I'm an academic and I get into it in the weeds. That's not really a meaningful definition necessarily. It just kind of born out of convenience. It's a nice round number. As there's a textbook that puts it really well, that there's no flash of green light when you go from Mach 4.9 to 5.1. It's not something special that happens. Really what we're thinking about is this is flight. Velocities are very, very fast, faster than a mile per second. And then what happens is you're moving so fast, so you get extremely hot temperatures on the surface of the vehicle, approaching the temperature of the surface of the sun potentially. And when you're hitting the air that fast, you can actually start to dissociate the molecules, rip them apart, strip off electrons. And so you get this chemically reacting shock layer that's very thin and sort of hugs the surface that can become a plasma layer that's no longer got the composition of typical air anymore. And it's an extremely harsh environment, whether it's, you're talking about tracking or having telemetry or communications, and even keeping your vehicle alive. So dealing with the heating in that harsh environment is really becomes your #1 design driver. How do you get something that's survivable, that can do what you want it to do, and that you can maneuver? So it's really challenging. And one thing I'll get into a little bit are generally testing challenges and how hard it is to recreate this environment on the ground without spending tens of millions of dollars on a flight test. And then there's also the propulsion side of it. You can get things going this fast with a rocket. That's how we almost always do it. This isn't that new of a field, right? We were doing some of our first hypersonics tests in the 1940s. So really shortly after we had rockets, we were flying things at hypersonic speed. ICBMs all come in at Mach 20-ish, so they're hypersonic. What's really novel, and from a geopolitical sense, are these hypersonic systems that fly in the atmosphere for a long time, where they're low enough where they're hard to track with radar. Probably going to have to rely on space-based sensing of these systems, and they're maneuverable. So they become very difficult to intercept and track and predict exactly where they're going to end up, because they can fly around in the atmosphere potentially for a long duration. And that's a very different type of technical problem, to have something that can survive for that long. So that's sort of what we're dealing with here. And then on the propulsion side, like I was saying, you can have a rocket to boost something to that speed. And that's not relatively novel. But if you want something that can really sustain itself in the atmosphere for a long time, like an aircraft or even like a cruise missile, say, you need to have some sort of air-breathing propulsion system. And those are very low maturity, very low technology readiness level right now. Things like scramjets, ramjets, rotating detonation engines. We haven't seen a lot of that, right? So, to give some more context on this number, we've got your commercial jets that you generally fly on are kind of Mach 0.7, 0.8. Fighter jets are about Mach 2. It was funny. Somebody said and made some headlines. They made a claim, a Boeing engineer, that the F-15 could hit Mach 3, which sort of raised some eyebrows. And then they very quickly walked that back, because the turbines in the airframe just really aren't built for that. So a traditional gas turbine, it's really hard to go more than Mach about 2.5. But on the other end of things, space shuttle or anything up in orbit, when that hits the atmosphere, it's about Mach 25. You get into this weird place with the physics where Mach number maybe doesn't have a lot of meaning in a certain part of your reentry regime, but sort of ballpark, that's what we're looking at. And if you're coming back from the moon, Apollo, Orion, it's Mach 30 plus. All right. So we're talking about things that are moving very, very fast. Now, there's a lot of motivation to be able to ground test these things, because it is it's a real challenge to create this environment. And like I said, if you do a proper flight test, it gets expensive fast. A single flight test would build you a really nice wind tunnel facility, okay? Because $10 million is a cheap flight test of a vehicle, and that's kind of sounding rocket type scale test. And on the computational side, I mean, it's 2024. We have a lot of computing power that we didn't used to have, but even still, these problems aren't particularly tractable. They're multi-physics. When you've got some of the heating issues happening, and some of the chemistry going on, it's a coupled multi-physics thing that's really challenging to get right from a simulation perspective. And we don't have the experimental data even to anchor those models. So we are still heavily reliant on ground test measurements. But even those are imperfect. There's no are high enthalpy ground test facilities or hot facilities, because like I said, in this true flight environment, hypersonic regime, you have an incredible amount of heating, which becomes one of the defining factors of a hypersonic system. So one way that we can do that is with an arc heated or plasma jet facility, and there are very few of these in the world. Really, only a handful in the United States. You really just this large arc in the plasma facilities. It can be inductively coupled plasma, which works in a similar way, but you're creating a lot of heat flux that can actually be representative of reentry conditions. These are pretty much the only way that we have where we can reliably test space reentry materials or these high temperature ceramics and ablators. So these run for a very long time, but you're talking tens of thousands of dollars, per second sometimes, these become very expensive tests. You're in a range of $1 million a week for these types of runs. But that makes them, given that there are so few, lead times on these facilities, if you showed up at NASA Ames and wanted to test your material and you made your down payment, you're probably testing sometime in 2026 if you start planning today. So the long lead time, which isn't ideal, and one other kind of complicating factor is the chemistry is very complex. So you've got this plasma that is not particularly well characterized. Even the centerline conditions, a lot of times, are not well known for these facilities, which, of course, if you're talking about doing model validation, makes things difficult because you don't even know exactly what your boundary conditions were. So then we have this other class of heated blowdown facilities where these are going to be slightly lower Mach number than the ones in the top left here. Because these can hit sort of reentry heat flux conditions. The heated blowdown facilities are maybe Mach 5 to 10 type range. They can still run for a long duration. What I mean by long duration with both of these is minutes at a time. And you can hit a lot of relevant conditions, but again, they're very expensive. The NASA 8-foot high temperature tunnel and the AEDC BKF tunnel that you see here, similarly, 2-year wait times, $1 million plus per test. There are only a handful of places in the world that operate in this way. And then the chemistry can be kind of messy because usually the way that we generate the heating is through some sort of burning or a vitiated process. And that, you can play some tricks where you replace oxygen and try and clean up the combustion products, but ultimately you usually don't have something that's exactly air, which makes things challenging. So there's limitations to these facilities as well, and you can't hit your entire flight envelope. So, and also I'd like to point out in terms of scale, none of these are testing full-scale flight articles. I mean, the NASA tunnel here is an 8-foot. That's an 8-foot opening right there. That's about as big as you see. So maybe something on the scale of a cruise missile, you can test it full size, but that's about it. You're not putting a spacecraft in one of these, for example, or an airplane. Continuing around here, sort of counterclockwise, we've got ballistic and sled facilities that you can use, and so you can put several miles of train track out in the desert in Arizona and strap some rockets onto a test article and test that way, which that works. You're starting to approach flight tests in terms of cost and repeatability. with things like this. But it can be a sort of reusable system. You get very high temperatures. You can get just about any type of test condition you want. You're still going to be limited in the size of your test article that you can run. But now you've got a moving model. How do you instrument that? How do you record all the data you want? You're not going to be able to see everything that you see in a lab. There's only a few places in the country that do this kind of testing. And then obviously, in many cases, this is a destructive test. You lose your model at the end of it. It's tricky to recover things with a test like this. So if you're going to instrument, you might not get those instruments back, and you might need to read them off while this thing is in flight. And then one other direction that we go for high enthalpy tests to get these hot conditions are shock expansion facilities. And so these are impulse facilities. They run very short duration, maybe millisecond to hundreds of microseconds that you actually are on condition. You can get just about any type of relevant hypersonic condition you want, and you can get those reentry heat fluxes. But because the test is so short, you're not actually looking at thermal response of the material. So you don't really do material testing in this. They're more aerodynamic focused with the right type of chemistry and aero conditions. All right. But you've got, like I said, very, very short run times, which presents their own challenges and potential for chemical non-equilibrium because that shock heating happens so fast. Sometimes the molecules effectively become frozen thermodynamically and aren't exactly representative of what you have in flight. So there's a way around that with an expansion facility, but now you're looking, again, something that's very specialized. There's only a few in the country. So what we did at UTSA, all of these facilities are very complex. They all come with their challenges and still don't quite hit the mark. So to have something that students could actually run on campus, we actually went low enthalpy. So we said, let's not worry about the heating side of it, and let's focus on the aerodynamics. So we can do high Reynolds number and high Mach number up to Mach 7.2. Actually, we can hit Mach 11 if we switch the test gas to helium. But we built this tunnel on campus, like I said, mostly built by students. It's what's called a Ludwig tube facility. It makes it a lot more accessible. And compared to facilities where you're looking at costs of like maybe $1 million a week, we have very, very low overhead here. A single test really in terms of raw materials costs as little as $10 or $15. So it's an 8-inch by 8-inch square test section. That's right here. The way that this works, you have high pressure on this side on this long piece of pipe, low pressure here in the vacuum section. And the nozzle, when you basically got a diaphragm here that you pressurize this air up until that metal diaphragm pops and bursts open. That allows the high pressure air to rush through the nozzle into the vacuum. And then we test here, this nozzle shaped just like a rocket nozzle, for example, expands that air out to high speed, and we get Mach 7 conditions here. The test is limited by how long it takes for an unsteady wave system to move down the length of this pipe. That's why it's so long, and then bounce back and then come back through. That gives us about 100 milliseconds of test, which might sound short, but it's a lot longer than what you get in an expansion tube or a shock tube. And when we image everything with high-speed cameras that can frame up to 2 megahertz, it's actually a really long time. When you play things back at 30 frames per second, like you're used to watching movies, we get 10 or 20-minute videos of what's happening during steady conditions in our flow. So we get lots and lots of data. We can turn the facility over very quickly, really in about 20 minutes. So we can, this says 2 to 4 times a day. It's probably more than that now. I think our record is 7 or so. Most of our time usually is not limited by the facility. It's limited more in changing out our experimental setup, messing with optics and cameras and stuff, because we do a lot of advanced diagnostic work. And I kind of like to point out, all right, this is real. We built it. I see a lot of stuff like this where, you know, they're kind of PowerPoint facilities. It's something that's aspirational, but whether or not it ever actually happens, who knows? We've been running this for a while. We've had over 600 tests since we built this thing 3 years ago. So it came on really well and has been a real workhorse for us. And like I said, the students are the ones that have ownership of this facility in my eyes. They built it, they operate it. That was kind of part of the design, and that was part of the motivator for why we went low enthalpy. It was going to make it easier for the students to work with and train on, but it's given us a capability where we can do some very relevant aerodynamic measurements, as I'm going to show you, without worrying about some of the more complicated physics that you deal with that are not always tractable. Also, I'd like to give some context here for, the sort of the gap that exists in hypersonic tests. Now, a few of us there are. It's a small community. So in the U.S., there's about 20 places that are doing active hypersonic ground tests. And this includes our national labs, universities, NASA centers, et cetera. Now, if you limit this to universities, there's about 13 doing hypersonic tests with tunnels at M greater than 5. And then at places with a Mach number above 7 that they're capable of testing, there's really 6. And I'm kind of being generous. A couple of these aren't particularly active. So it's a very small group. And we've gotten a lot of press about this. We've been in the local news. There's a Real Engineering video. If any of your students like that channel, check it out. We've been on CNN and have a bunch of good social media outreach. So it's been fun, the positive reception that we've gotten for this tunnel. And so what we do in this lab, it's about half our portfolio are fundamental fluids measurements related to aerodynamics, and about half are really focused on developing those measurements. So we do a lot of both. And then when we've got these high-speed measurements, a lot of laser diagnostics and imaging that happen, you're getting gigabytes of data for every shot. That requires a bunch of statistical analysis just to pull a thread to understand what it is that you're seeing in the data set, and a lot of image processing. The students probably spend more time writing code than they do actually conducting their experiments, because once they get that pile of data that they're sitting on, they've got to make sense of it. So that ends up being a good chunk of our time too, is developing those analysis tools. And a big focus, like I said, is on developing these measurements, which is not necessarily straightforward. I tell people, anytime you can measure something at Mach 7, it's a big deal, because that's a hard thing to do. For a long time, because I kind of alluded to, we've been doing hypersonics since the 1940s. So this is not a new flight regime, but a lot of these measurements are new. Because for a while, we were sort of limited to point probe-based techniques. You have a pressure sensor that you scan around or something like that. But in these facilities, some of the ones I've talked about, and in our facility as well, whether you've got plasma and high temperatures or the run duration is short, you don't want to be restricted to scanning something. Also, if you have an intrusive probe, then you're changing what you're measuring. Some of these probes won't hold up in certain conditions. So it's appealing if you can do something non-intrusively with optics and light and cameras to measure not just a single point, but an entire field of view, or maybe even a three-dimensional field of view. That becomes very powerful. We didn't do this for a long time just because of the limited availability of the technology, but now high-speed cameras and high-speed lasers are becoming commercially available, which has made these things much more tractable. So we do use a technique called Schlerin imaging. That is sort of our bread and butter first thing that we throw at something that is pretty reliable, just to do visualization of the flow. That's what you see. This is just an air jet right here, but you're going to see some examples of this in the tunnel. We do a lot of free flight testing where we actually cut a model loose in the test section, let it fly for that 100 milliseconds. And then the nice thing about the free flight testing is you can get your forces and moments. I'll talk about that in a second. We've got a technique called planar laser induced fluorescence, where we introduce a chemical tracer into the flow, and then we can tag it and track it with a laser and a camera. That's really great flow visualization on the surface, but you can turn that into things like pressure, temperature, mole fraction if you understand the chemical well enough. You can also track where the molecule goes in this technique called molecular tagging velocimetry that I have a slide on here in a second. We do velocimetry with our lasers using a technique called particle image velocimetry, and we even develop pressure and temperature sensitive paint in-house. And I've got some slides to talk about that briefly also. But really, overall, the big picture is with the various non-intrusive techniques that we have, sort of our mantra is if someone wants a measurement, we have a way to do it. And pretty much any quantity of interest you can dream up, there's probably a way that we can measure it. And if not, then that's a proposal I want to write because I want to make sure that we can measure everything in this tunnel that we want to. So molecular tagging velocimetry, I like to highlight this one first because it's really elegant and simple and works extremely well. Basically what we do, we introduce a fluorescent tracer into our test section. And one of the advantages of a Ludwig tube facility like this is we can just put it in our driver tube gas and then it's everywhere all the time. And so what we do, then we create a laser line through our test section when the tunnel's running, and then we mark this this species. We basically tag a line. And then the nature of that fluorescence, and we're actually realizing this is phosphorescence given the long-lived nature here, is once that laser is turned off, you continue to see the fluorescence and the phosphorescence from the chemical species. So that there's a lifetime from the phosphorescence that's on the order of hundreds of microseconds. All right, so it hangs around for a while. And then what you see here are multiple exposures on our camera of this line basically as it's marching downstream. And you can see the intensity is decreasing as the lifetime fades out. But we get this tagged line moving through a test section. All right. And so then you know the change in time between your camera exposures, and you know the change in distance between those lines because you did do a calibration with your scaling before you run the test. And so if you have delta X and delta T, then you can get velocity, and so you can get these pretty well resolved free stream velocity measurements this way. But you can even do it in a boundary layer as well, and you see these classic boundary layer profiles developing as these lines march through in your boundary layer also. And that's actually lined up reasonably well with a bunch of our other techniques and pitot probe measurements also. So we published a paper on that. That was really nice. Like I said, we do the free flight testing. There's a bunch of different ways that we're able to do this. The simplest, so this is just a bouncy ball. And we literally just take a piece of floss or fishing line or string and super glue it to the ball. And then when the wind tunnel starts up, that pulls the thread away. And then you just have this free flight test article. And the time scale of gravity is very, very small relative to the aero coefficients here. And so what happens is when we do object tracking with these models, and if you know your model's mass and you know your delta X and delta T again, over successive images, not only do you have velocity, but you have acceleration. And so if you have mass and acceleration, then you can get all of your forces and aero moments and coefficients. For non-symmetric models, we can get pitching and things like that. So this is a sphere. It's the easiest case, but we realized pretty fast that the string approach really only works well when you have a model that's symmetric and you don't really care about its orientation. So something the students developed was this kind of swinging gate mechanism, as you see here. You basically have a little saddle that you build, and this is just a 3D printed plastic part, and it's on a hinge. When the tunnel starts up, you can see this hinge falls away, and then that leaves the model in the test section to fly by itself. And you can do more complicated geometries. This is supposed to simulate a tumbling rocket body. We did some stuff for NASA's Orbital Debris Program office to get some drag coefficients for a variety of different rocket body shapes, for example. We have an electromagnetic release, and that works okay also. The main issue is whatever the electromagnet is, you need to get it out of the way fast enough, and that becomes a little bit tricky, which is why we kind of rely on this method with the swinging gate a lot. The other clever thing that the students came up with was a styrofoam release, where you basically, like you see here, you get a big piece of styrofoam and you cut a hole to hold the model. And then when the tunnel starts up, the styrofoam breaks and falls away. And this was some testing that they did that was representative of the NASA Dragonfly concept. And so they've got a mission they're planning to send a drone to Titan, which is pretty awesome if you ask me. And the students heard about this and they got excited. We also realized that even though our tunnel is cold, we actually represent the conditions on Titan really, really well. And we can put a little bit of methane in our test section and pretty much match that atmosphere identically. All right. And so we were able to get some stability measurements for NASA on a Dragonfly capsule, which was neat. And I need to speed up because I got a lot of slides left and I got about 10 minutes. So one thing, this is from the Joint Hypersonic Transition Office. We're looking at separation events. So there are a lot of different cases where you can imagine one body separating from another body at very high speed that we would care about, whether it's like a store separation, a booster drop, a stage separation, or even like a shroud opening up. There's some very complicated aerodynamics at play that are difficult to capture and model. And this is one of our projects that's CUI, so we can't share the results, unfortunately, because there's some really neat stuff. But this has been a fun project to work on. We're in year 3 of this one, and it's gone really well, just looking at the aerodynamics of things that are flying apart. Let's see, we've got a hypersonic jet and crossflow problem that we're working on. Basically, when you're flying this fast, flaps and fins don't tend to work, especially when you're up in the upper atmosphere because of complex interactions that get generated. So you're relying on reaction control jets. Just like the space capsules when they're docking with the space station or something like that. But the issue is you get down in the atmosphere and you start flying and you're moving at Mach 10. Suddenly those jets have a really strong interaction with the oncoming flow. You can actually get negative control moments relative to what you're supposed to have because of the aerodynamics there. It's not super well understood. There's some pretty complicated things that happen. You can generate a lot of heating. So we're making measurements of these jets to better understand what's going on and try and give some data that can anchor some modeling as well. Another fun one is we're working with a collaborator here that develops what's called architected materials. And they actually build and 3D print materials with a unit cell architecture that can give you sort of custom tailored properties. And so one example that we have is you can damp certain frequencies based on how you design these unit cells. And there are some cases in like a high-speed flow where you have some unwanted oscillations that maybe we would want to damp. And so we designed one of these materials to target that frequency, put it in the tunnel, and generated a we sort of forced that oscillation that normally you wouldn't want, but we wanted to show that it was there. So we created this oscillating shock wave and then placed the material in the vicinity of that shock wave oscillation. And we actually were able to show that it damped that interaction. And so then we got some funding to pursue that further. And now we're working on version 2 to iterate on that further and try and further improve the technique. Another one that we're working on that's NASA funded is this thing called the FAST full airframe sensing technology. I talked about how expensive flight tests are. Like I said, $10 million is a cheap flight test, but you're limited in how many sensors you can actually pack on a flight vehicle and how much data you can extract from that thing while it's in the air. So we kind of want to do as much as we can with that sparse sensing network. And we asked the question, well, if you can use modern artificial intelligence and machine learning tools to connect the dots between a sparse network of sensors, would that actually give you something useful? And so, because there are a lot of instances where maybe you have a limited number of pressure sensors or temperature sensors on the flight article, and then we started gathering some test data. That's our role at UTSA, is to get the truth measurements. And then we've got collaborators at the University of Texas that are actually doing the AI ML work and trying to sort of fill in the blanks of those data sets. And then you can ask yourself, well, if you can extend that problem to get, say, pressure or temperature everywhere on the surface from a sparse network, can you then further take that inverse problem to get something like stress on the surface? Or if you have pressure, temperature, and stress now, could you extract velocity off the body if you know enough about the flow physics? And so that's been a really fun one to work. we've been using this technique. I think I have a better slide here in a second to kind of talk about it more. But we paint these models with pressure and temperature sensitive paint, which is paint that we make in-house that actually responds to changes in pressure and temperature. And we actually see, here's a better one, we actually see the pressure distribution and the temperature distribution on the surface of the model in real time. And so every pixel of your camera becomes a pressure or temperature sensor. And it's fast response as well. It's unsteady. You know, it's several kilohertz. So we can actually see fluctuating quantities in the pressure as well. One other one I was going to highlight is this Air Force project where we're looking at shockwave boundary layer interaction physics, basically in a high-speed flow. Anytime you have something sticking off from a body, even if it's a fin or a control surface or a flap, it creates a shockwave in front of it. I was kind of alluding to this undesirable unsteadiness, and a big part of that comes from shockwave boundary layer interactions. They can oscillate at several kilohertz, create some really harsh acoustic and thermal loads on a vehicle. There's even some historical incidences, say with the X-15 flight vehicle ripping off a pylon on a test article. So they can really do some serious damage if they pop up in a place you didn't want, or if they behave in a way that are unexpected. We've spent, 60 years studying shockwave boundary layer interactions, still don't understand them as well as we would like. And we realized a lot of these hypersonic systems are going to have non-smooth surfaces. They're ablating, they've maybe got tiles or some sort of roughness. Almost all the shock boundary layer interaction research that we've done in the past is using polished, smooth stainless steel surfaces, which really is not representative of a true hypersonic system. So now we're starting to dig into what happens if you have something rough. We used a carbon fiber template to sort of make a comparison. The big takeaway that we had are these interactions are very, very different. Things scale by about a factor of 10 for the rough case. It totally changes what the interaction looks like. This is smooth on the left, rough on the right. We do, and here's smooth, rough. You can see how different this interaction becomes. The dynamics change. We're able to track the shock wave with some image processing that the students do, and get PDFs of the position, get all this unsteady data, which then you can turn into spectra. You can see the frequency content changes considerably. But there's some ways you can scale things and start to get them to line up. So we're starting to understand this better, work towards a predictive capability. And actually, we've been working with Microsoft on some AI stuff that they wanted to do to speed up the shock processing code and see if, and they've actually done it by about a factor of 10 using AI tools. So that we're kind of exploring that also, which is interesting. And then, we compare this to surface pressure measurements. Again, everything very high speed. These are megahertz response rate surface pressure sensors. And then compare that again to the pressure sensitive paint I was talking about. You can see it here. It looks, sort of bright, hot pink when you illuminate this stuff in the lab. And like I said, you just image this paint with a camera and you're going to get a response that corresponds to pressure changes on the surface. All right. And so this is what we see on the back end of that compression ramp. There's a shock wave here. You can see in the Schlieren, this is kind of the side view. All right. So the shock wave is coming up here, and then the flow separates, and then it reattaches, and then you get these streak structures on the back end where the pressure comes back and hits very fast. And you see it look a little bit different for the rough case, but these are responding at kilohertz rate in our hypersonic wind tunnel, in that kind of 50 to 100 millisecond test time. And from a fluids perspective, what we're actually seeing here are these little vortices that roll up along the backside of the compression ramp there, which are, exactly why they're there is something that, I have arguments with about people. The folks in this community, we kind of argue about it over dinner when we see each other, like what exactly is going on. But there are a bunch of groups seeing the structure now that we're getting higher resolution data with the tools available today. And people aren't exactly sure what these are, what they're coming from. But that's kind of probably a big part of tying up this whole shock boundary layer interaction problem. We can even do oil flow, where you quite literally, you take some very thin oil and put some fluorescent dye in there and coat it on your surface, and then you run the tunnel, and you get what's left resembles the flow features near the surface. I love this stuff because I think it provides a really striking visualization. The students hate it when I ask them to do it because it makes a mess and then they have to spend an hour cleaning it up later. So they're always, trying to not have to do the oil flow, but every now and then it's nice to do because, again, you see these vortices, just like we saw in the pressure-sensitive paint, that pop out. You can see some recirculation and separation region here. So you get a lot of interesting structure that pops in really what's a pretty straightforward application. And then, I don't want to, I need to wrap up, so I don't want to get into this too much, but you see these vortices that we can do a bunch of different types of analysis on it using some various tools. And we did this with temperature sensitive paint as well at different heating conditions. And you can see the same structure evident in the temperature case too. All right. But because of the nature of how temperature actually behaves, how it interacts with the model, you don't see rapid responses the same way that you do pressure because there's some capacitance basically in the model, right? And yeah, that lends itself to heat transfer analysis. You can get heat transfer coefficients. One of the interesting things that we saw is that for the rough surface, the heat transfer rates are considerably higher. Kind of part of the big story that we're seeing. The rough interaction was notably different. And we can tell it's definitely something that people are going to have to account for when they're designing a vehicle. I feel like in these presentations, a lot of times we tend to only show the highlights, but for every good image that people see, there's probably 10 where things didn't work out. So I kind of like to remind folks of that. It doesn't always go as planned. On the left here, somebody didn't strap down the carbon fiber on that model the way that they were supposed to, and then that got ripped apart at Mach 7, made a big mess. Here on the right, somebody was trying to apply oil flow to one of our vehicle geometries, and I don't know what happened with the mixture here, but we pulled the vacuum, the stuff bubbled and ballooned, and that was a mess. So this kind of stuff we deal with. It's a process, right? Especially, and these students are learning. What we do, we've done a lot of fun stuff. Do some fun demos in the tunnel with students, but a Cybertruck and a U-Haul and a cow in there. Some of the things that we're moving towards next, we've got a high-speed IR camera that's going to allow us to do temperature measurements very fast. That's coming in April. We're doing more velocimetry. We're working towards what I'm calling 4D imaging, where we can get 3D images that are time resolved with our laser, which nobody's ever been able to do it in a hypersonic condition. And this thing we're going to start using this thing called an OPO, which is an optical parametric oscillator that allows us to tune our laser to different frequencies, basically see different things, and keep tuning the pressure sensitive paint, temperature sensitive paint formulations too, to make them better. Because like I said, we are making those here on campus ourselves. Companies that'll sell it to you, but we figured out how to make them. So we've just been doing that. And then, yeah, we do, the high-speed cameras are fun, right? They allow us to do a lot of different things. Look at a variety of different types of flow features. I didn't even get to talk about our detonation tube that we have, where we did some rotating detonation engine research, but we've had some fun there too. So I think, yeah, this is probably it. These are some of the other fun ones too. This is popcorn at 10 kilohertz. You can see the kernel open up. We've done some drone analysis. We did a COVID thing, pop balloons with lasers. So there's a lot of fun stuff we've gotten to do with the cameras. I do really like the popcorn one. I feel like that's pretty relatable. Everybody has popcorn, right? And getting to see the kernel open up at really high speed is kind of a neat thing. So with that, I want to, especially, it's late for you guys, so I want to make sure we end on time, but leave a couple of minutes, for questions there. So what I'm actually going to do, let's see, let me leave this up, but hopefully I can hear audio, and if people jump in with questions, in this way I can flip the slides if I need to. But thank you guys again for staying up late and for your attention here today.
Thanks a lot, Chris, for the very interesting presentation on what you're doing at UTSA and also your work on hypersonics. Hypersonics have been in the news a lot lately. We've been hearing about, seems like there's a proliferation of hypersonic, say, weapons in recent years, even though the field, as you mentioned, has been around for close to 6 decades or more. Would you say there's been some key reason why there's been a sudden surge in the proliferation of hypersonic vehicles or missiles in recent years? Was there some key technological breakthrough that allowed this, or is it just sort of the natural progression of things?
I don't think it's necessarily key technological breakthrough, at least from the US standpoint. But I think just to give you some background on some of the geopolitical factors, I mean, so the US, we flew the X-15 back in the late 1960s, and that was a crude Mach 6.7 aircraft. All right. And we don't have anything like that today. And nothing, there's no crude vehicle that has surpassed that speed since then. So we were setting records that still stand back in the 60s. This isn't new for us. Basically, the US with hypersonic systems got to a point where they said, we don't see a ton of utility in the mission. And you sort of hit a point, like I said, where things get really, really hard. There's a big step up in degree of difficulty when you talk about going from something like an ICBM that just has to survive to impact after a brief period of time in space and a relatively short time in the atmosphere, to something now that is going to live in the atmosphere for a while, fly maybe like an airplane, maneuver, needs to have an air-breathing propulsion system. That's a big set of challenges. And from where I sit, understandably for a very long time, there was not, when you have the number of, say, nuclear weapons on the table, you know, what's the need for something that can evade a radar if, you know, nobody's going to stop a nuclear arsenal anyway, right? So that was sort of the thinking for a long time. More recently, I think Russians, in maybe a little bit out of concern that the U.S. was going to be able to intercept a nuclear weapon, became more motivated to develop something that could evade air defense and radar. And so they started to push in that direction. I think China was thinking the same thing. So they were looking for something to give them the upper hand over the U.S. arsenal. And now, from a U.S. perspective, we realize, well, if they're going to have that type of capability, there's some thinking that we would like to have it too. I think also China is interested in something that can be a standoff weapon that can go after carriers and that type of thing. So so now, even if the U.S. wasn't concerned about an offensive capability, you need a hypersonic weapon probably to intercept a hypersonic weapon, unless you go directed energy and do it with a laser. And I think there's also a use case now that we're considering, you know, just for conventional type things. If you have a high value target, or if you need something to get from one place to another very fast, there's some justification and motivation to do that. So it's the type of thing where I think technologically, at least for the US, it would have been possible a long time ago. And then we sort of didn't see a lot of utility in making that next technological step. But then recently, sort of Russia and China have caught up and have gotten to a place where they felt like they could go after it. And that sort of pushed everybody else to pursue it also, if that makes sense.
Okay, I see your point. Thank you very much for that explanation. I also noticed from your slides, you mentioned that you're currently getting together a group of faculty members across a very diverse range of disciplines, both in the sciences and the different fields of engineering, for your aerospace program. And I'm wondering, I assume most of these faculty were already present at UTSA before you guys started. So what sort of work have you been doing in terms of trying to get everyone together and function and build an integrated department using everyone's backgrounds and expertise?
Yeah, I mean, that's interesting, right? So some of that has happened through the CAMI Center I was talking about. We have a unique structure with our centers and institutes where basically if proposals get awarded that are connected to a center, the center will get some money returned. And so we've kind of used that to help motivate people. Hey, write your proposals through this center, then we can pool all that money together and do some neat things with it. We can help out students. We can pay for some other stuff, do some events. And so that's kind of been a catalyst to bring people together, get everybody routing stuff through the center. And then we're able to host events, get students in the same place. That further fosters collaboration and gets people talking, gets people in the same room. Yeah, I think that's really been a big thing, is just pulling everybody together and having a lot of events, bringing in seminars from people from different areas, just trying to generally raise awareness. I think that's part of what we deal with. I'm sure you've experienced the same thing. When you're at a big university, there's so many people here doing so many different things, and a lot of people don't know what else is going on. And so just trying to get everybody together and raise awareness of, hey, this person over here is doing this, they're interested in these areas, and sort of create that mapping and that community. That's sort of been the big thing. So a lot of it is just even just having some food in the same place and having an interesting technical discussion to bring people together has really made a difference. And then I think sort of connecting through the center to pool resources and really build that way has been great.
Okay, thanks. I'd like to open up the floor to any audience members who have questions. If you have a question, please feel free to turn on your mic and go ahead, or raise your hand. And if you don't mind, if you could introduce yourself and your affiliation when you ask a question, just so we have a better idea of where you're coming from. Okay, York, I see you've raised your hand.
Hi, thank you for introducing me. Hi, Dr. Combs. I'm York from Taiwan Space Agency. So we're working on a hyper rocket launch vehicles right now.
Very cool.
Me myself personally, I'm your fans from Twitter. So I've been Twitter account for quite a long time, and I also looked at the videos from the real engineering also. So
great. Yeah, that was fun.
Video, yeah. So I'm trying not to make this discussion becomes too nerdy. So I want to ask a question about what's the role played by public sector on building the hypersonic wind tunnel from UTSA? Because NASA didn't, I mean, how did NASA or Air Force contact you? Did they contact you directly and say, okay, let's build a wind tunnel? Or what's the whole story? Because I understand that public sectors really need to support academia research like this, and a wind tunnel like this. We don't have such wind tunnel in Taiwan here. So yeah, I'm pretty curious about the whole story here.
Yeah, I mean, actually, so the public, I guess in the sense that you're talking about, public sector was not a part of this. So I came to UTSA in 2018, and the tunnel itself was entirely funded with UTSA dollars as part of my startup package. So that was something I negotiated when I came. They gave me the lab space and they gave me the money to build it and to renovate the space. All in between $1 and $2 million probably to build the tunnel that we have, which is pretty cheap for the capability that we came out with. I've seen things that I feel like are less capable that were an order of magnitude more expensive. We had a lot of students build it. We designed everything ourselves and just outsourced some of the custom manufacturing that we couldn't do. But it came together really well. I had the advantage of the fact that I had already helped build 2 wind tunnels before this one. So I'd kind of learned a lot from that. And I'd worked on another wind tunnel as a grad student, actually a few other ones as a grad student. So I'd been around a lot of them. I kind of had the confidence that we knew how to design this thing and build it. So yeah, it was entirely UTSA startup that funded it. I think in terms of the public sector involvement, that was really more of just, I had some awareness of the current landscape. I knew that there was a need for this type of thing. I felt like there was demand, and that sort of if we did build it, I knew that the public sector would be interested, right? And that's been 100% the case. So in the sense that NASA and Air Force were actively funding a lot of hypersonics work, they contributed in that way, and they've definitely provided funds for projects and research and students and equipment since we built the tunnel. But the tunnel itself and the initial groundbreaking of the project, that was actually entirely UTSA.
Thank you. So it's more like a do the right thing at right time, I would say.
Yeah, there's a lot of that. And I mean, I still think there's a need for more facilities. I mean, we're testing all the time, and I think there's more people could be testing. We actually just got some funding to try and build a pilot for for a high enthalpy tunnel. Can't talk about that one much right now, but that's something to keep an eye on later. And so that'll be a neat thing once we get it going. But yeah, there's definitely, I think people think they're more expensive really than they are, and it depends on the scale of facility that you can build. You don't need to have $100 million to build one of these, but with a couple $1 million, you can really make a difference, I think. Which then it becomes something on the scale that maybe a university can support.
Okay, thanks, Chris.
Yeah.
Are there any additional questions from our audience members? One more question, just out of curiosity. So when you're mentioning the Mach number, you're mentioning that's the ratio between the velocity and the speed of sound. But since the speed of sound is influenced by is inversely proportionate to the density of the fluid, do you guys achieve higher Mach numbers by adjusting the density or pressure of the working fluid, or is that not something that you typically do?
That's a great question, and something I like to clarify to people when I'm giving tours of the tunnel, because it is a little bit counterintuitive. But the way it actually works out is our Mach number for a fixed test gas is entirely determined by the area ratio of our nozzle. It's the way the math works out. And so, because what happens is you do what's called, you choke the flow at the constriction of the nozzle at the throat. Sorry about my dog there. And so you go down to that minimum constriction, and that's Mach 1. And then the air expands back out, and that's when it starts to accelerate. And so we expand it out to a ratio where it works out to Mach 7.2. And then for that case, changing the back pressure cannot change the Mach number further, because you can't go past Mach 1 at that constriction. So you're stuck, you're choked. And what it does, it just changes your mass flow ratio, which is really means your Reynolds number is going to be different. Or in other words, it's like you're changing your altitude. So you increase the pressure on the back end, and it's like you're flying lower, really. So the only way that we can change Mach number is we can change the nozzle, which we have not done yet. We've been using one nozzle the whole time, but we could, in theory, machine a new nozzle that would give us a different Mach number with a different geometry, or we can change the test gas. And so, kind of like I said, you run helium. It's a lighter gas, you get a higher Mach number. So we're Mach 11 when we run helium, and then you could do like a helium air mix and get Mach numbers in between.
Okay, thanks. It's very interesting to see how these hypersonic velocities are attained.
Yeah, it's a fun problem.
Okay, okay. I think we have a question from Mr. Wong.
I'm Yuzhen from National Central University. I'm a master's student in Department of Space Science and Engineering.
All right, great.
So my question is, what's the advantage for public to develop hypersonic technology in atmosphere, except for the military use like vehicle or missile?
Yeah, that's a good question. There's some context I think I missed at the front end probably that I should have included. So, as it's easy to focus on the military side, whether it's offensive or defensive capability, but there's a lot of other reasons people pursue this. And so we've been dealing with hypersonic flight in space flight for a long time, right? So kind of like I was alluding to, anything up in orbit, it's effectively going Mach 25 without getting too deep into the physics. Once you get inside the atmosphere on a reentry, that's a hypersonic flight problem. So getting things back from space safely requires an understanding of hypersonics. If you want to land something on Mars or on some other extraterrestrial body, that's a hypersonic entry problem. So you need to understand that well. And then even on the ascent stage, you can hit Mach 5 on the way out at a time when that's relevant. So getting rockets out of the atmosphere too, that matters. Even on so I kind of mentioned we had done some work for the NASA Orbital Debris Program Office. Space junk is a big problem, right? And there was a lot of news last week from that ESA satellite that re-entered uncontrolled. And those predictions are really hard to get right. usually the best we're going to do is about 1 orbital period. And we usually don't know when they come down for a while. And we could do better if we had a better understanding of hypersonic aerodynamics, because the space junk reentry issue is a hypersonic aero problem. And so if you can understand those couple of physics, then we could have a better feel for how space junk is going to return also. And then the other side of it is the long-term potential for high-speed commercial transport, which is really interesting. There's some companies working on this. Hermes is one here in Atlanta, Georgia, that's doing some really neat stuff. And so, you know, you could imagine going from, you know, say US mainland to Europe in about 90 minutes at hypersonic speed, really getting anywhere around the world in 1 or 2 hours. That's a pretty exciting thing to potentially be able to do. And, you know, even here in the United States, we can get entire US coverage in about 20 minutes from San Antonio at Mach 7. So really instantaneous interconnectedness for people. If we're able to harness this capability, that's got a lot of appeal as well.
Yeah. Okay. Thank you, Dr. Combs. And can I ask a following questions?
Go ahead.
Sure.
Yeah. Since you mentioned the high-speed commercial transport, so what is your thought between the hypersonic flight, commercial hypersonic flight, and commercial suborbit flight?
Yeah, I mean, that's an interesting one. I think probably I think there are some advantages to the suborbital or like kind of semi-orbital flight, or the hops. It sort of gets you out of the atmosphere and simplifies the problem a little bit. You just would have, it's basically a higher G experience all the way. And then to get up that high, you're going to come in hotter and faster. So you basically, you have a more intense engineering problem to deal with on the reentry and landing if you're doing a suborbital flight. But for a large portion of that flight, you don't necessarily have much to worry about. Whereas for the hypersonic aircraft, I mean, you could spend a lot of time flying very high in the upper atmosphere where maybe you save yourself a little bit, but it's that entire duration of the flight, you're experiencing those aerodynamic forces, but it's less extreme in any given instance than what you're going to have right at the reentry portion of a suborbital hop. So there's some pros and cons I can see to both. I think the suborbital thing is closer given current technology and our experience with things. Hypersonic commercial aircraft is farther away, but it'll be interesting to see where those go. Hopefully that answered your question. Okay.
Yeah, thank you so much.
Okay. Are there any additional questions for Dr. Combs? Okay. So if there are no additional questions, I'd just like to ask one more follow-up. So in terms of international collaborations on these different topics, are there any particular domains that you'd be interested in collaborating internationally with at UTSA, or and are there certain topics, for example, defense related, that are a bit more restricted in nature in terms of who you can collaborate with?
Oh yeah, I mean, I'm definitely interested in collaboration. I think there's a lot of opportunity. The thing that I tell people, because hypersonics, it can get touchy, but usually we're okay and things can be sort of open and public access as long as we stick to the fundamental physics. Once you start talking about specific geometries and specific flight systems or specific real materials and things like that, then you can start to run into issues and collaboration starts to get harder. But if we keep things mostly sort of public domain and focus on the foundational physics or development of really novel things, then it's generally not a problem. There's certain funding agencies that basically anything you do hypersonic, they want to make it controlled. But a lot of the ones that we work with are not like that. So there's plenty of room for collaboration, just as long as we don't pitch the connectedness of something to like a very specific vehicle geometry. It's generally okay.
Okay, thanks. That's really good to hear, and hopefully there's plenty of room for future exchanges and collaborations between institutions here in Taiwan and the work you're doing at UTSA.
Absolutely, and I mean, because I have a lot of U.S. citizens in the lab, and there are projects that are U.S. citizen only, but I have a handful of international students and an international exchange student working right now. So that, yeah, there's definitely precedent for that and something that I think is important to maintain.
Okay, excellent. Good to hear. Are there any last questions for Professor Combs? Well, if not, then thanks a lot, Chris, for waking up early, and thanks to everyone in the audience for staying up late. And hopefully this is the beginning of a series of exchanges and collaborations between institutions here in Taiwan and UTSA.
All right. Thanks again for the invite. Really appreciate it, everybody. And yeah, good night. hope
Thanks
you get to sleep all right.
Okay. So good morning and good night, everyone.
Yeah. Okay. All right. Take care, guys.
Bye-bye.
Thanks a lot.
Thanks a lot. Bye bye.
Yeah. Thank you.
Bye bye.